In this video, we're going to go ahead and cover section 10.4, still part of Unit 10, Topics in Analytic Geometry. And this is hyperbolas, and it's the last conic section we're going to talk about, and then before we get into rotation of conics, which is the next part. So a hyperbola, what is a hyperbola? It is a set of all points x and y in a plane for which the absolute value of the difference of the distances from two distinct fixed points, which are the foci or the focus points, is constant. So I don't actually have that picture in particular here, but I'll show it to you in class. Basically, it's the distance. If I were to take, let's say a point right here, the distance from here, from this point to this focus, to this point to this focus, will be constant no matter where. So if I keep moving the point up, that triangle that it's going to, well, somewhat triangle that's going to form, will be constant, okay? So here's what a hyperbola looks like. It's kind of like two parabolas almost. And it looks like this. It can be sideways, it can be vertical. So this one that we have right here is actually a horizontal one. And you'll notice I did label a few things here. For this one, what we have is we have this axis in the middle. It's called the transverse axis, and it is equal to 2a, where a is basically the distance from the center to the vertex of the hyperbola, or the vertices of the hyperbola. We do have two vertex points, one for each side, and of course this is a, which gives us our 2a. Okay, the focus point for this is going to be kind of on the inside of the hyperbola, so out, or outside, however you want to think about it. Um, and then we do have our distance C, just like we did before. But this time the C is actually going to be bigger than our A because it's from the center to the focus point. So it looks like what I have labeled here. Okay, and there is a B value, but we'll talk about the B value in just a bit with one of the examples. Just like I mentioned, C is the distance from the center to the focus, and the vertices are A units from the center. We also have this C squared is equal to A squared plus B squared, just like Pythagorean theorem, right? And there is a relationship between that, by the way, but we won't talk about that in this video. But just because we are going to need C and B for other other parts of this, okay? Let's go ahead and look at some more definition stuff. We have the standard equation of a hyperbola with the center of HK. Two different options. Okay, we have the horizontal, which is basically all this, and then we have the vertical, which is basically all of this. If our center is something besides 0, 0, then we look at these cases where you have x minus h squared over a squared minus, the y counterpart, and vice versa if it's vertical. One thing to note here, and I did not put it here, but I guess I should have, is that in the previous unit for the ellipse, basically the one that had the bigger one, the bigger number on the bottom, that's basically what told us if it was going to be vertical or horizontal. For this one, A can be greater than B or it can be smaller than B. It doesn't really matter. Um, what matters is which one comes first. So if your x comes first, it's going to be horizontal. If your y comes first, it's going to be vertical. Okay, it's just a quick note. And of course, if the origin is the center, then h and k kind of disappear because we're just 0, and we're left with these two forms. Okay, and again, here are some quick representations of what those graphs might look like. We have the horizontal where the hyperbolas are kind of like facing each other this way, and I did kind of label my A transverse axis here to A in blue. Focus points are equal to the following. If it is vertical, then you have them kind of facing each other, but up and down. That's one way to think about it. Okay, so I'm going to go ahead and show you some examples. By the way, these examples are all pre-done because this is kind of a lengthy, not that it's difficult, but it does take a while to copy everything. So I went ahead and just took the liberty of solving everything for us, and we're going to explain, okay? So example number 1 is asking us to find the standard form of the equation of the hyperbola with the following vertices and the following foci points. So what I did first is I went ahead and graphed it, and you can see that right here. So I went ahead and graphed everything. It says that we have our vertex points of 2, 2, 2, and 2, -4. I went ahead and just put V and V for those. And then the focus points are a little bit outside of that, so 2, 3, and 2, -5. Okay, so what I did with that is I went ahead and since I know my vertices, I went ahead and found the center, which is right in the middle. There's a distance of 6 units between this point and this point. That's what I wrote here. So that means that the center would be 3 units in. So if I count from here, 1, 2, 3, I end at this point right here, 2, -1. So my center is 2, -1. And that also means that my A value is going to be half of that total distance. So 6 divided by 2 is just 3. So A is equal to 3. And I kind of wrote that here. I also know that my C value is the distance from the center to the focus. So since I was given the focus point, that's going to be basically 3 plus 1 is 4. So C is equal to 4. Okay. And finally, for this one, since we can see that it's a vertical hyperbola, we are going to use this format of the equation where the y is first because that's what gives us a vertical hyperbola. So all I have to do now at this point is find b because I know that I do have a b square. So I went ahead and used my formula. C squared is equal to a squared plus b squared. We're solving for b, so you kind of have to think, well, if we're solving for b squared, we want to move the a squared over. So we're going to use it like this, where you subtract a squared from both sides, and we end up with c squared minus a squared, which is what I have right here. Again, c equals 4 equals 3, which I found here and over here by just, counting. So we plug it in like so, and we get that b squared is equal to 7. Okay, so the reason I went ahead and wrote it like that, you'll notice that right here, I put b squared comes out to 7 because 4 squared is 16, 3 squared is 9, 16 minus 9 is 7. Or you could do b equals square root of 7, but the formula asks for b squared, so I'm just going to leave it as b squared, yeah, which is 7. And that is basically all I have to do because now I have everything. I have my center was 2, -1, which again is right there, 2, -1. So that means I have plus 1 for the y because it's kind of the opposite, and minus 2 for the x because my x was positive 2. Plug in my a square, which is 9, 3 squared is 9, and then plug in my b square, which again is 7, and that is it. Okay, that is it for the first one. Let's move on to the next one. Again, these are pre-done. So hopefully this video does not come out too long. Let's actually, I'm sorry, we're not covering the example yet. We have another kind of definition, I guess. We have asymptotes of a hyperbola. I bet you thought you were done with those, but you're not. So asymptotes of a hyperbola. What's an asymptote? So an asymptote, just a quick reminder, is kind of like this imaginary line or, well, yeah, we'll just say line. Imaginary line that the graph will get very, very close to. Um, and that's the quickest way I can explain it, yeah, without going into too many details. So what we're going to do here is we're going to find the equations of the asymptotes, and this does have asymptotes. The asymptotes are diagonal in this case, and it's basically the part where we can kind of draw our curve against. I probably should have drawn this a little bit more curved, but this hyperbola will kind of, get really close to this line, to these lines, I should say. And there are two of them because, well, it's kind of like a cross section, right? So we have, if it's horizontal, we're going to use this one. If it's vertical, we're going to use this one. And then we have this picture over here where you kind of see like a little box being drawn. Yes, we can use these equations, but honestly, it's a lot easier, I think, if you just kind of do a cross section. What I mean by that, well, if in this case, this is a horizontal representation. If you know the distance of A, remember A is from here to here, we just got to double it, right? And that gives you the length of the box horizontally. And this is where B comes into play. B is actually going to be the other axis. It's called the conjugate axis. And whatever the value of B is, it's basically B units up this way, B units down this way, a total of 2B. And if we have that value, we can create this rectangle or this box. And our asymptotes are going to be going from one corner to the other. So once you have this box, you can just, kind of put a straight edge and just draw your asymptote. So, and we're going to do it both ways just so you can see that it does work out. But yeah, so let's go ahead and start an example. for how to find asymptotes of a hyperbola, we have sketch the hyperbola 4y squared minus 9x squared is equal to 36. So the first problem I see with this is that it's not equal to 1, and I don't see any a squares or b squares. So I am going to rewrite this first. Let me let's do that. Yeah. We're going to rewrite this first. You'll notice right here on the rewrite, I divided everything by 36 because I want this to equal to 1. And that gave me y squared over 9 because 4 over 36 is 1 over 9. And x squared over 4 because again 9 over 36 simplifies to 1/4. So we're left with this right here. And from here, I have a lot of information. I have basically all this. So let me explain this part. Okay. Since we have no parentheses on the top, that tells me my center is 0, 0. Since my y is first, that tells me this is a vertical hyperbola. I have a squared underneath the first term, so it's 9 squared. So a squared is 9, which means that a is equal to 3. B squared is the second one, so B squared is 4, which means that B is equal to 2. And then this is just kind of an FYI. In case we needed to find the C value, you would use your, C squared is A squared plus B squared, add them up, and then square root. So this is kind of extra, but it's good. It's always good to have a little bit more information. And then we're going to go ahead and use all that to graph our hyperbola. So here it is. Let me cover this part first here. You will notice that I do have my center here at 0, 0. Okay, so there's my center. I guess I should label that with a C, center. And I know that since this is a vertical hyperbola, and my vertical, I guess you could say my transverse axis is 3, from here I went up 3. So 1, 2, 3, and there is one vertex point at 0, 3. And then I went down 3, 1, 2, 3, and there's my second vertex at 0, -3. Okay, and again, this part right here is what we would call our transverse axis. So this right here, I'm going to kind of do it in blue. This whole part right here, well, not the transverse. Well, yeah, I guess you could call it that. This is the A. This is the A value from this piece. This is A. This is A. Total of 2A. So where does B come into play? Well, I know that B is equal to 2. Okay. So what I'm going to do is from my vertex, I actually go over 2 spaces, 1, 2, and it kind of lands right here, and then 1, 2, and lands right there. And you'll notice that I do have this box kind of lightly outlined. And the box was created basically from these 2 points, so my vertex points, and then wherever my B value lands. So in this case, the 2's. So I have this box, and once I have the box, what I literally did is I took and I don't actually have a straight edge. I just kind of I used this. I'm going to shamelessly, not that I'm advocating for Naruto or anything, but this is what I used. I went from corner to corner. So I went from this corner to this corner, and I just kind of drew a line. Yeah, I drew a dashed line um, this way and then this way. By the way, this is, I believe, Sasuke's headband, just if anyone's interested. And then, yeah, there's my 2 asymptotes. So um, once I have the asymptote, you'll notice that my curve for the hyperbola is just kind of lean against those lines. And then same thing down here. Here on the side, I went ahead and did show it algebraically just so you can kind of see what's going on. So the formula for a vertical hyperbola, the asymptotes for that is y equals k plus or minus a over b times x minus h. So I plugged everything in. My k was 0, my a was 3, my b was 2. Again, h was 0. Work this out. So the 0 is gone. The 0 is gone here. We're left with plus or minus 3 over 2x. So if we were to pick like 2 points on this asymptote, the positive one, that means the slope should be 3 over 2, right? So 1, 2, 3, 1, 2. It works out. And the same backwards if you look at the negative ones. So 1, 2, 3, 1, 2. So again, it works out perfectly. You can do it this way. You can do it this way. Personally, I think this is easier. Whatever you prefer to do. Okay. Let's go ahead and look at another example. We have a total of 5 examples, guys. So trying to go a little, not too fast, but not too long either. Example number 3 is a complete the square problem. Cover that real quickly. It says sketch the hyperbola 9x squared minus 4y squared plus 8y minus 40 equals 0. And there's kind of a glare coming in here. There we go. So I'm going to show this in steps, I guess. What I did first is I want to just rewrote it. And then I moved my constant over. So you'll notice that the 40 is now positive 40. And from there, I rearrange things again. I notice that my y is the one that has, I have the y squared and the y. So I'm going to take the 4 out and see if that's helpful in any way. And I'm left with y squared minus 2y, because if you divide out negative 4, 8 divided by negative 4 is negative 2. Okay. The x does not have any other x's with it, so we're actually just going to kind of bring it down. We're not going to add anything to that one. Here's the complete the square part, where you have to add b over 2 squared to both sides. So in this case, my b is negative 2. So negative 2 divided by 2 is negative 1. I square that and I get a 1. And that's exactly what I added. So usually I box here, same, you get it. So I added a 1 to both sides in the parentheses here, plus 1, and this is a positive 1. You will notice that I put a negative 4 here, and it's not just there randomly. The reason I have that negative 4, like I mentioned in one of the classes, is because this is actually being multiplied by negative 4. So we can't just do plus 1. You have to do plus 1 times negative 4, because whatever you do to this side, you got to do to this side. So that's where that negative 4 is coming from. We factor. So this right here comes out to y minus 1 squared, because y minus 1 times y minus 1 is y squared minus 2y plus 1. Okay. And then over here, I just changed that to minus 4 just to show the steps. I went ahead and subtracted 40 minus 4 is 36. And then we're going to rewrite this part like this, because again, remember, we want that 1 on the right side. So I divide everything by 36 and I end up with my equation. So 9 over 36 is again 1 over 4. 4 over 36 is 1 over 9. And then from here, I can get all this information. I can get that since x is first, it's going to be horizontal. And this is where I was talking about where A can be less than B, you'll notice that the 4 is smaller than the 9, which is fine. It happens. For hyperbolas, it happens. But what we're looking at for the orientation is what comes first. The x comes first. So A squared is 4. And that means A is 2. B squared is going to be 9, which means B is 3. We have a center of 0, 1 because we have nothing here, but we have a negative 1 there. So 0, 1. And then again, our c squared, we just add these two up and square root, which is square root of 13. And the last thing you had to do with this one was actually sketch the hyperbola. So with all this information, you can do that. Here is part of it, and we're going to go ahead and finish that part together here. You will notice that I have my center at 0, 1. I went ahead and did since I know that A is going to be 2, I went 2 spaces over. So 1, 2, 1, 2, and that is my A part, which I cannot find where did I leave my pen? Oh, here it is. Okay, so this part right here is the A part that I keep talking about. That's A. And then the other one's going to be my B, which came out to 3. Where is it? B is equal to 3. So you'll notice from here I went 1, 2, 3, 1, 2, 3, and that's where this box comes from. Okay, so once I have those 4, I guess you could say kind of points. You don't actually put a point here, but guidelines. We can go ahead and do our asymptotes, which I'm going to do again here. You're going to see exactly how I did it, going from corner to corner. So something like that. And it will go through the center and through the outer parts of my little box, of my rectangle. Okay, so there's one, and here is the other one. I'm going to get it as straight as possible. You know me, the perfectionist. So something like that. And if it's not perfect, that's fine. I'm actually not that much of a perfectionist. But anyway, so there we go. We have our asymptotes. Again, this is one of the asymptotes. We'll just kind of put ASYMPT. And that means that my hyperbola is going to kind of hug these really closely. So this is my vertex, one of them. So that means it's going to go something like, maybe like that. And this one, something like that. Okay, same thing with this side. We're going to go ahead and just hug that curve like so. And there is a pretty decent sketch of our hyperbola. Okay. All right. Example number 4. We're almost done. Example number 4. Oh, you know what? I did not do this part. Yeah, I guess I'm going to do it real quickly. So algebraically, real quickly, we're going to go ahead and do that. We have y is equal to k. Our k value is actually going to be 1. So 1 plus or minus. My b value is 3. So 3 over a value is 2. So 3 over 2 x minus h, which in this case is 0. So we have y is equal to 1 plus or minus 3 halves x. In other words, if I were to graph these two lines, you would have a slope of 3 over 2 starting at 1 with a y-intercept of 1. So if we look at this line right here, for instance, we have a y-intercept of 1, and then 1, 2, 3, 1, 2. So we're good to go. It works for the other one as well. Let's do one more, well, not one more, we have 2 more examples actually, but they're pretty simple, so hopefully they don't take too long. We have using asymptotes to find the standard equation. So here is the problem. Okay, let me try to get this a little bit better here. It says find the standard form of the equation of the hyperbola with vertices 3, 2, and 9, 2, and asymptotes, those two that we have right there. Okay, so how did we do this one? So what I did is I graphed it. I went ahead and graphed the vertices, and then I tried to do the I tried to solve for B and A. That's what I did. So here below, you'll see kind of a little bit of a mess here. So here is my first point. This is 3, 2, and this one is going to be 9, 2. And just by the orientation, because they're, kind of, you have the same y values, I can tell that this is going to be a horizontal hyperbola. So I put that here on the halfway point between these two. Remember this distance right here, this is 2a. So the halfway point would be our a, and that's going to give us right in the middle of the center 6, 2. So you'll notice there's my center labeled. Since it's horizontal, I'm going to use this notation. So again, here is one of the equations. And I only have to look at one of them because if you notice, this part right here is just the part that's talking about the y-intercept. The part that I really care about is this part because that's where I have B and A, okay? See, B and A. So what I did is I just kind of wrote one out and I said, well, if this is the case, well, my M, I put M1, but it's actually going to be both of them. I guess we can do that, equals. So our m is going to be based off of these numbers. So m is equal to 2 over 3. That means that b is equal, I shouldn't put the x there. I'm so sorry. There's no x. So that means that b is 2 and 3 is a. And that is basically it. So once you have your a and your b, here's the equation. We have that our center was 6, 2. So that means we have x minus 6 squared. And again, the x comes first because this is a horizontal hyperbola over a squared, which is 9 because a equals 3, so a squared equals 9. I should have maybe done that. And then y minus 2 because again my y value is 2, so we have y minus 2 in the equation over our b squared, which turned out to be 4. And that's all there is to it, to that one. Finally, we're almost done. We have eccentricity. So this one also has eccentricity, just like the ellipse had it, where that one determined ovalness. This one determines, I guess you could say, how flat or not flat the hyperbola is going to be. So it's still measured as E equals C over A, but this time E can be very, very large. Basically, anything greater than 1 is considered large. So when E is large, you're going to have this kind of case where the hyperbola is like almost like a flat line, and we call these the branches. I don't know if I mentioned that earlier. It's labeled in the diagram, but this right here is a branch. This right here is a branch. So you want to maybe put that here. It's in the first picture you drew, but if you want to put it again, that's fine. This is also a branch. So the branches are very well, almost flat, right? That's if your E is bigger than 1. Okay, we say E is large. If its E is close to 1, so it's kind of small, well, the branches get like squished, right? And they look more like this. You'll also notice that the focus points, are affected by that. So if we have a large eccentricity, the focus points are farther away. If we have a small eccentricity as far as being close to 1, the focus points are pretty close to the vertex points, to the vertices. All right, last one, and then that's it. This one we're probably going to do in class because it's not that difficult, and also goes with the time. So, but what you need to do for this one is actually copy this stuff down first. This last part, since this is the last type of conic that we're going to see, I want you to be able to classify a conic just kind of based on the equation. So we have the following conics: circle, parabola, ellipse, hyperbola. The circle we covered last semester, so if we need to review it, we can definitely do that in class. But it's the easiest one. So you will have these graphs in this format usually, and this is what happens. If A is equal to C, so these are the same, it's probably going to be a circle as long as A is not equal to 0. If A times C is equal to 0, so in other words, if one of these is equal to 0, not both, just one of them, then it's a parabola. If A times C is greater than 0, so this times this, if you multiply them and it gives you something bigger than 0, and also if they have the same signs, that means it's an ellipse, okay? And it has to have the same sign because for multiplication, if it's two positives, it's positive. Two negatives, it's positive. If you have different signs, well, then it becomes negative, right? And we have the hyperbola case where if that does happen, well, it's a hyperbola. If the signs are different, this is going to come out to negative because that's what happens when you have different signs. So get that and then go ahead and copy this real quickly. We'll do this part in class. It will not take long, I promise. And this is going to be basically classifying the graphs of each of these equations. Just classifying, nothing further than that. That's it, guys. That's it for this video. If you have any questions, as always, please let me know.